Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So today we're going to talk about testing, and really, it's not just, it's like Paul Carter alluded to, it's a little more than what you think it is. So really, we're going to go through, why do we test? Kind of the types of tests we can do. Then, why do we test? It's sort of a good question to ask, because then it helps you lead us to choosing the type of testing that's appropriate. We'll then sum it up with some TRM differentiators.
Okay, well then, to get started, why is testing such an important component of TRM's work, and what are the primary approaches?
Yeah, so really the key here is to understand the unit's performance over all the operating conditions, and really to make sure that the part will operate effectively and in spec over its entire life. That's really why we do it. So what approaches do we take? We go in there, we measure key characteristics and key performance indicators on the parts. We then go in there and we measure those performance indicators in various environments. By doing that, we can characterize the way we expect parts to change in environments, if they're going to change at all. And then we can then, from there, make determinations, really what do we want to test on every part, or which can we have that's going to be a sort of test that's going to be representative of how that unit's going to perform over its life. The other thing we do also is that clearly, if parts have to operate over 20 years, we can't wait around for 20 years to see whether or not they're going to meet life. So there are various compression algorithms that are used to simulate full life in a much shorter period of time, basically by overstressing the unit and doing things like that. We can simulate a lower stress environment over a longer period of time by using certain mathematical compression algorithms to approximate the total life of the part.
Okay, well, that makes sense. And do you also test for various electrical things?
Absolutely. Electrical testing is usually the one thing that most people think of first, as far as, when you go into test, especially for microwave components, is do the parts meet all of their key requirements? These sorts of things are tested typically on a VNA, an ENA, or a PNA type of network analyzer. These TRM tests these parameters 100%. And what we then do is we then go in there and we record the data off of the analyzer, and this is the data that we can then go in and manipulate to determine whether or not it meets all of the requirements, whether it be tracking requirements or phase matching requirements. A lot of that analysis is done off of the analyzer in a separate calculation sheet. Usually a spreadsheet is what TRM uses very often to do those sort of mathematical comparisons, just to verify that yes, it meets all the requirements, as part of as it comes off the line, to make sure that yes, it is absolutely compliant.
Got it. And how about mechanical testing? What about that?
Well, that's the second half of the equation, Paul. So the mechanical testing, and does it meet all of its dimensional requirements? For some applications, can be just as critical as the electrical requirements. TRM has two CMM machines, like the one in the photo here. These are used to inspect to very high accuracy the mechanical dimensions of the part and the interfaces of the part, especially when you get into blind mate connectors or other features where we have to check for flatness and perpendicularity. These sorts of features are can be checked at 100% of the level to verify that yes, the parts do meet those requirements. Not all parts require this, but TRM certainly has this capability in-house, and it's something that we do routinely.
Okay, well, that makes sense. How do environmental considerations fit in?
Okay, so environmental testing is really, sort of kind of where the rubber meets the road here as far as the design is concerned. It's one thing to design a part that will meet the requirements at room temperature, sitting on a bench. It's another to say is, will it meet these requirements, and will it survive these requirements over its service life in the field? So the very first thing that we think about here is thermal screening. A lot of components have solder joints. Solder joints tend to be a low cycle fatigue sort of failure issue if there's going to be one. Therefore, we go and we do thermal cycling to simulate life of those solder joints. Also, you see there we have TRM owns two vibration tables, so we can go ahead and we can dynamically test these parts to make sure that we do the shake, rattle, and roll test to make sure that the parts will survive those environments. Both of these sorts of testing, whether it be thermal testing or dynamic vibration testing, is also done as part of ESS testing. Now, what ESS testing is that the thought is that 90% of the failures that you're going to see due to environmental conditions will happen in what we call infant mortality, which basically it'll happen within the first few percent of its life. So as part of ESS screening, what we do is we actually take up a couple percent of a component's life by putting it through some stress early on to make sure that to try to weed out those infant mortality parts. So that again becomes a very common sort of thing for us to do here at TRM. As we go through this now, it's not just, will the part survive these environments, but will it operate over these environments? What's pictured here are some of our advanced ENAs and PNAs that we have here at TRM. As you can see here, we've modified thermal chambers so that we can actually measure performance of parts while they're at temperature, and we can characterize those performance at temperature. Or whether it's during vibration, we can monitor insertion loss during vibration. There's lots of things that we can do here at TRM to verify that these parts will indeed operate per spec over the environments. It's a very important thing to go to make sure that they do operate over these environments.
Okay. Now, I've also heard you speak about analysis. How does that differ from testing?
Sure. Now, analysis is there's two ways to look at analysis. One is you do analysis to give yourself confidence going into the actual test. Nobody wants to go into a test and not know whether you're going to pass or not. The whole idea of going into these tests really is just to verify that your analysis, that yes, the parts will be compliant. You don't want to go into a test with a completely unknown. That's not very good risk management. The other way we use analysis for is there are some tests that are quite frankly very expensive to use, or the analysis is so good that really the testing becomes unimportant. So the first case there, we'll talk about expense, especially on parts for spacecraft, multi-paction, corona breakdown. Those sorts of tests are quite frankly very expensive to run. The analysis to do those is fairly robust, and if we can show significant margin, many customers will forego those tests in an effort to be a little more efficient with their budgets. The other thing that is done is analysis, for example, like fungus growth. Those sorts of parameters are so well understood that if those materials are not in the part, it really makes no sense to run that test. It's a very long test to run there, and it's quite frankly, it really eats up a lot of schedule to actually run that test. And if there's no known elements in the component that will feed a fungus growth, or that can be a fungus nutrient, and quite frankly, there's no sense in running the test. So, and those are a couple of cases there where analysis would be done in lieu of an actual test. The other thing also that we look at here from an analysis standpoint, and sometimes this is coupled with some environmental testing, is how will the unit perform over manufacturing tolerances and over different environments? With some sample testing or some data, very often you can go in there and you can extrapolate out what will happen over manufacturing tolerancing with the part based off of some room ATP type data. You can go in there and you can extrapolate what will happen over the life of the part or over some more extreme environments.
Okay. And I've also heard you refer to different stages of testing. Can you explain?
Sure. I mean, I've been kind of alluding to that all along here. Basically, there are three main stages for testing. Once a part gets designed, we then go through, as part of its design, we do a lot of the analysis to make sure that we give ourselves confidence that we will indeed that we do indeed have a part that will meet all of its requirements over all of its environments. Well, how do we verify that? The first thing we do is we go into qualification testing. Qualification testing will have us measure the unit, perform over essentially all of its environments, and try to simulate that the part will survive over its full life. So what do we do here? We will take date over temperature to verify the thermal characteristics. We will go in, we will do vibration, we will do thermal cycling to make sure that the part will survive and be compliant over all of its operating environments. Very often we will do TVAC testing and other sorts of testing involved to make sure that we don't have any kind of corona events. There's leak testing. There's all kinds of things that we will go through there to make sure that the part is indeed meeting all of its requirements. The one thing caveat about these tests is they're quite extensive, and they will essentially at the end of the testing, the part will be at the end of its life. So we will actually go through it and test the part essentially until its useful life is used up. So in that case, qualification testing is destructive in the fact that at the end of the testing, even if the unit completely passes, there is no real design life left in the unit, so it really can't be used after that. The next category is acceptance testing, and based on the qualification testing and based on the data that we get out of there, a subgroup of testing that is non-destructive will be selected to test on 100% of the parts. This is typically electrical testing and electrical testing to meet the electrical parameters, as well as dimensional measurements to make sure that the part dimensionally meets all of its requirements. The third category is is used as in tandem with the acceptance testing, and it's called environmental stress screening, or ESS testing. And really what we're looking for here is to make sure that by doing this testing here is we're taking a couple percent of its life out of it by running it through some thermal cycles, running it through some light vibration in order to find those manufacturing anomalies that could lead to an infant mortality in the screening of the part and in the life of its part, to make sure that we don't have any issues in the field. So the three main groups there are really, we go in there, we beat the unit up, we make sure that it can meet its life. We then, as units are come off the line, they go through a combination of environmental stress screening to make sure that we don't have any manufacturing defects, and then and then we go ahead and we test these parts 100% for electrical testing and mechanical dimensions to make sure that they're compliant to the drawing.
Got it. As always, lots of good information, Shaun. Would you like to summarize?
Sure. So quickly, what we have here is really operating over all of these environments is critical. It's a rare day when parts in our field are operating in a room environment where it's a nice, comfortable 70 degrees, low humidity, and no vibration. So we have to make sure that these parts operate over the environments that they're going to be used in. Planning the testing is actually quite important, and just try to determine which tests are appropriate at which stage of development. It's not always appropriate to test for every parameter on every part being built. It's not very cost effective. It can actually damage the parts because some of the testing that is done to verify some of the environments, quite frankly, is destructive. So we have to make sure that plan is set up to make sure that we test the appropriate feature at the appropriate time on the appropriate part. Something else that's critical is that, especially for a lot of high-rel military space programs, is that the objective evidence that the testing was done and how well did it meet the requirements. It's not always a black and white, did it pass or did it fail, but supplying that objective evidence, so this way here everybody can go in there, look at the data to determine whether or not how well the part did at whatever stage of testing was being completed. So the objective evidence is quite important, and something that TRM always supplies with our parts.
Okay. And what are some of the differentiators with respect to testing and verification specific to TRM?
Sure. So, TRM, first of all, we like to work with our customers. This is a key differentiator for us. We love to talk to our customers, find out really what it is they're doing, what's important to them, and in this way here we can make sure that we design the best part and the best fit for their system. This also gives a good opportunity to go in there and find out really what environments are these tests going to be in, and what's most critical about that. Very often there's trade-offs that need to be made. Having an informed decision certainly makes for a better product for everybody. Knowing all this, we can go in there, we can carefully select materials and make sure that we have the optimum solution with very much unique, robust packaging in order to meet the environments. And TRM is always happy to supply the objective evidence for all the testing that gets done, whether it be environmental testing or electrical testing. TRM is not just a part provider, we're a solution provider, and part of that solution is data.
Okay, excellent. So we have a couple of questions. I know we have time for at least one. And I wondered about this too. Don't all custom manufacturers in the field perform testing and verification?
Yes, they do. But it's a matter really of whether or not they farm it all out or whether they can have control of that and do it in-house. TRM is fully vertically integrated. Most testing that is required for our types of products, we have that capability in-house. As a result, we can custom modify all those tests for our product and for the specific needs of the customer. We are not just going out and running a straight mill standard testing at an outside house with no ability to modify that testing or do whatever specific for the program. As a result, that's a big value add, the fact that we do this all in-house. We have complete control over it, and we can really test right down to exactly what the customer requires for whichever stage that we're at.
Okay. Well, thank you again, Shaun, and thanks to all of you for joining us. If you are a customer and you have more questions, or if you'd like to discuss details of one of your programs with one of our engineers, we'd love to hear from you. You can call our engineering hotline. The number is on the screen, 888-677-6877. There is no cost for these calls. If you're one of our field sales representatives, then you know your calls are always welcome too. And you can submit questions directly through the sales rep portal, which is on our website. So once again, thank you all. We hope you'll join us for the next Tech Talk, which will be in the July timeframe, and more information to follow. Thank you, Shaun.
Thank you, Paul.